Good morning. I'm Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, SRM Institute of Science and Technology. I welcome you all for the tutorial on design of absorption column. In this video, I'm going to explain about the design calculations on packed bed absorption column and plate type absorption column. Let us move on to the video. Problem statement: a solute is to be recovered from a gas stream by absorption with pure water in a packed column. The entering gas stream contains 2.5% by volume of the solute and the leaving gas contains 0.1% of solute by volume. A liquid rate of 1.5 times the minimum rate is to be employed. The equilibrium data is represented by the equation y is equal to 0.15x, where y and x are the mole fractions of the solute in gas and liquid phase respectively. Calculate the minimum solvent to gas flow rate, actual solvent rate, and the composition of solute in the leaving stream of solvent. So when you read the problem statement, first you have to check which type of equipment is given in the problem condition, whether it is a packed column or plate type absorption column. So in the first statement is clearly mentioned that it is the packed column. And the next part, what is the gas mixture and which solvent is used for separation. So in this it is given that a solute is recovered from gas stream. So it is a general way, it is just mentioned as solute which is separated from the gas stream with pure water in a packed column. So that means water is used as a solvent, and it is also mentioned that it is a pure solvent. That means there is no presence of solute in it. So in the given statement, it is that in the problem statement is given that 2.5% by volume of the solute in the entering gas stream. So the gas stream that enters from the bottom section of the absorption column and it leaves from the top section, and solvent is introduced from the top section of the column and leaves from the bottom section of the column. So when the solute and solvent are made into contact with each other, the solute that gets dissolved in the solvent and that is carried away by the solvent in the leaving stream. So in the problem statement is given the 2.5% by volume of solute. So that means in the inlet stream of gas mixture, 2.5 mole percentage of solute and remaining 97.5 percentage of some inert components are present, and the leaving gas contains 0.1% of solute by volume. So in the leaving stream, solute concentration is 0.1% and remaining 99.9% is inert component. So by assuming this is an ideal gas mixture, whatever volume percentage given, that can be taken as the mole percentage of components. Then a liquid rate of 1.5 times the minimum rate is to be employed. So we are supplying liquid, the solvent, for getting the separation of solute. So the solvent flow rate is 1.5 times the minimum rate. So whatever theoretically we need from there, 1.5 times excess we are supplying as the actual flow rate of solvent. Then the equilibrium data, y is equal to 0.15x. So the composition of solute in gas phase and liquid phase at equilibrium condition, that is represented by the expression y is equal to 0.15x. So that means the equilibrium line is a straight line and y and x are mole fraction of solute in gas phase and liquid phase. So you are asked to calculate the minimum solvent to gas flow rate. L minimum by G. So the ratio between minimum flow rate of solvent to gas flow rate and also the actual solvent rate in terms of ratio L actual to gas flow rate, and finally composition of solute in the leaving stream of solvent. So these are the three parameters we are asked to find out. First, let us write the data given in the problem statement. So we are given with the 2.5% by mole percent of solute. So from there, mole fraction is 0.025. So YB refers mole fraction of solute in the inlet stream of gas. Then 0.1% is mole percent. So in terms of fraction, which is 0.001, which is YA. So that means mole fraction of solute in the exit stream of gas. And the solvent used is pure solvent, I mean pure water. So solute content in the pure solvent is 0. So XA mole fraction of solute in the inlet stream of liquid, that is taken as 0. The first part we are asked to find out minimum solvent to gas flow rate, L minimum by G. So this can be calculated through material balance equation based on solute. So what is that equation? B into YB minus YA, that is equal to L minimum into XB star minus XA. So in this expression, V refers gas flow rate, I mean molar flow rate of gas, which can be taken as G, and L minimum is the minimum solvent flow rate, YB mole fraction of solute in the inlet stream of gas, YA mole fraction of solute in the exit stream of gas, XA mole fraction of solute in the inlet stream of liquid, and XB star is the equilibrium value of solute in liquid phase corresponding to YB value. So in this expression, we'll check what are the data we have in order to find out L minimum by V. So YB, YA, these two are given data. XA, that is also given, and the XB star. So XB star is the equilibrium value corresponding to YB. So how to obtain this value? So we can make use of the equilibrium equation given in the problem statement. So in that, if you substitute YB, the X which you get through this equation is XB star. So the next step of calculation is XB star in order to get L minimum by V. So we are going to use the equilibrium line equation that by substituting YB, you will be getting XB star. So XB star is obtained through equilibrium line equation. Next, you can substitute the value in the material balance equation and all the other parameter in this equation in order to find the ratio L minimum by V, which is L minimum by G. So which is coming around 0.1439. Next part of calculation is actual solvent rate. For this calculation, we can make use of the statement or condition given in the problem, which is liquid rate is 1.5 times the minimum rate. So minimum rate we know. So actual rate is 1.5 times more than that of minimum rate. So that L actual is 1.5 times the minimum L. So the next step of calculation, so L by V ratio, actual flow rate, so which is 1.5 times the minimum, and that is coming around 0.2159. And last part of calculation, composition of solute in the leaving stream of solvent. So how to find out the composition of solute? That means mole fraction of solute in the exit stream of liquid. So again, you can make use of the material balance equation. B into YB minus YA, that is equal to L into XB minus XA. So in that, we know L by V value, YB, YA, XA, all of the known data. By substituting all these data, the unknown parameter XB can be obtained. So which is coming around 0.1112. So next, let us move on to next problem. Problem statement, a solute is absorbed from a stream of air into a liquid solvent in a counter current packed tower at 299 Kelvin and 105 kilopascal. The terminal concentrations of solute in the liquid and the gas phase are X is equal to 0.0008, Y is equal to 0.0005 at the top, and X is equal to 0.152, Y is equal to 0.038 at the bottom. The equilibrium relation in terms of mole fraction is given by Y is equal to 0.19x. The individual height of transfer units based on the gas phase and liquid phase are 0.33 meter and 0.43 meter respectively. Calculate the height of packing. So in this problem statement, it is given that a solute is absorbed into a liquid solvent in a counter current packed tower. So that means we are given with the packed bed absorption column. In this, solute is separated by a liquid solvent at 299 Kelvin temperature and 105 kilopascal pressure. The terminal concentration, that means at the top and bottom section of the absorption column, concentration of solute are given. So concentration of solute, I mean mole fraction of solute in the inlet stream of gas, which is YB, and that is given as 0.038, and the mole fraction of solute in the exit stream of gas, which is YA, that is given in terms of 0.0005, and XA, mole fraction of solute in the inlet stream of gas, which is given as 0.0008, and mole fraction of solute in the exit stream of liquid, which is XB, 0.152. So all the terminal point concentrations, I mean mole fraction of solute in the inlet and exit stream of gas and liquid are given. And equilibrium relation is also given. Y is equal to 0.19x. So that means equilibrium line is a straight line. So you can say equilibrium line and the operating line are straight and parallel with each other. The individual height of transfer unit based on gas phase and liquid phase are given. That means Hx Hy and Hx data are given, and you are asked to find out the height of packing. So you have to find out how much is the height of packing required in order to achieve the desired separation. First, let us write the data given in the problem statement. So all the composition data XA, XB, YA, YB, let us write. Then equilibrium line equation, then Hx, Hy data, then the formula for calculating height of packing. So Zt, that is equal to NTU into HTU. So Zt is the height of packing, NTU refers number of transfer units, HTU refers height of a single transfer unit. So that can also be written in the form of NOY into HOY, where NOY refers overall number of transfer units based on gas phase, and HOY refers overall height of a transfer unit based on gas phase. So for calculating height of packing Zt, you need to find out NOY and HOY. So one by one, let us see how to find out NOY and HOY, and from there how to calculate height of packing. So first let us do the calculation for height of a transfer unit. So that can be calculated using the formula Hy plus mg by L into Hx. So the calculation of height of a transfer unit involves different forms of formula. Depending on the data given in your problem, you can choose the appropriate equation for the calculation of height of a transfer unit. So in this problem, we are given with Hx, Hy data. So we are using this form of expression for calculating HTU. So in this, Hy refers individual height of transfer unit based on gas phase, and Hx individual height of transfer unit based on liquid phase. M is the slope of the equilibrium line, G is the molar flow rate of gas, L is the molar flow rate of liquid. So for the calculation, we are given with Hy, Hx data. So that is the given data. M, which is slope of the equilibrium line equation. So the equation is y is equal to 0.19x. So M slope is 0.19. Then G by L. So the ratio, flow rate ratio of gas to liquid. So that is not given. So first we have to find out, then only we can calculate height of a transfer unit. So how to find out this ratio G by L? We can make use of material balance equation based on solute in order to find out G by L. The next step, number of transfer units. So that can be calculated by using the formula YB minus YA divided by delta Y bar L. So this simplified form of equation can be used only when the equilibrium line and operating line are straight and parallel. So in this case, YB, YA already we have discussed. Mole fraction of solute in the inlet stream of gas and mole fraction of solute at the exit stream of gas, and delta Y bar L is the logarithmic mean mole fraction difference, which can be calculated using the formula, given formula. So in that, YB star and YA star are the equilibrium values corresponding to XB and XA. So let us move on to the calculation. So material balance equation based on solute. So as I mentioned earlier, for finding height of a transfer unit, you need G by L value. So that can be calculated by using material balance equation. So what is that material balance equation? So G into YB minus YA, that is equal to L into XB minus XA. So instead of G, you can also use the notation V. So G by L, that can be calculated by rearranging this expression. Since all these four parameters are given in the problem, you can directly substitute this data in order to get G by L ratio, so which is coming around 4.032. The next, you can substitute in this value in the formula of HTU in order to get the value of HTU. So HY plus M into G by L, that is 4.032 into Hx. So the height of a single transfer unit is coming around 0.659 meter. The next step of calculation is for number of transfer units. Already I have shown you the formula. So for finding that, you need YB star, YA star data. So that YB star is the equilibrium value corresponding to XB. YA star is the equilibrium value corresponding to XA. So by substituting XB and XA value in equilibrium line equation, you will be getting the corresponding values of YB star and YA star. The next step, delta Y bar L calculation by substituting all the values of YB, YA, YB star, YA star in the formula. You can get delta Y bar L. Then by substituting this delta Y bar L, YB, YA data, you will be getting number of transfer units, which is coming around 13.99. Then the final step of calculation, height of packing, which is a product of NTU and HTU, that is 9.21 meter. I hope you have understood. We'll move on to the next problem. A gas mixture containing 10 mole percentage of sulfur dioxide in air at 1 atmosphere total pressure and 30 degrees Celsius is to be scrubbed with water to remove 97 percentage of sulfur dioxide. So the feed gas rate is 46 kilomole per hour. The total cross-sectional area is 0.781 meter square. The overall volumetric mass transfer coefficient based on gas phase is 270 kilomole per meter cube R delta Y. The slope of the equilibrium line is 40. Calculate the minimum solvent rate. If the solvent rate is 1.5 times the minimum, calculate the height of packing. So in the problem statement, it is mentioned that so the sulfur dioxide present in air is removed with water. So the solute which is separated from the gas mixture is sulfur dioxide with the help of water as a solvent in case of packed bed absorption column. We are given with concentration of sulfur dioxide in the inlet stream of gas. How much separation is expected, that is also given, and feed gas rate, that is the inlet stream of gas flow rate, that is given. The tower cross-sectional area, that is also given. Volumetric mass transfer coefficient based on gas phase, slope of the equilibrium line, and solvent rate condition. These are given in the problem and we are asked to find out height of packing. So as we did in the previous problem, for finding height of packing, you need number of transfer units and height of transfer unit. So we have to find out both NTU, HTU in order to find out height of packing. So first we'll list out the data given in the problem. So 10 mole percentage of sulfur dioxide is in the entering stream of gas. So from the mole percentage, the mole fraction can be taken, which is YB is equal to 0.1. And it is given that 97 percentage of sulfur dioxide is separated with the help of water. That means if I say 100 kilomole of sulfur dioxide enters the absorption column, out of 100 kilomole, 97 kilomole is removed by water, remaining 3 kilomole of that 100 that leaves in the exit stream of gas. That is the meaning of the 97 percentage sulfur dioxide. So in this case, if I take in terms of fraction, so 0.1 is the fraction of solute in my inlet stream. Out of 0.1, 97% of that 0.1 is separated by water. Remaining 3% of this 0.1 that leaves in the exit stream of gas. So that will help us to find out Ya, which is 3% of 0.1. That is Ya, mole fraction of sulfur dioxide in the exit stream of gas. And the gas inlet stream flow rate 46 kilomole per hour. And also area 0.781 meter square. Then volumetric mass transfer coefficient, slope of the line are given. We are asked to find out minimum solvent rate, and the solvent rate is 1.5 times the minimum. If it is so, then how much is the height of parking? So one by one, let's see. So that given data, let us write it. So slope of the equilibrium line, mass transfer coefficient, everything given, and the condition, everything will write. And we have to find out finally height of parking. So material balance equation based on solute will take for finding minimum solvent rate. So GM, that is the gas flow rate in terms of mole per unit time per unit area. YB, Ya are mole fraction of sulfur dioxide in the inlet stream of gas, exit stream of gas. Xa is mole fraction of sulfur dioxide in the inlet stream of solvent, and Xb star is the equilibrium value corresponding to YB. To find out L minimum, you need all these other data including Xb star, but Xb star is not given in the problem statement. So how to calculate that? So we are given with a slope of that equilibrium line 40, based on that y is equal to 40x. So by substituting yb in this equilibrium line, you will be getting xb star, that is that equilibrium value corresponding to yb star. So by substituting that, xb star is coming around 0.0025. Then by substituting all these data in the material balance equation, you will be getting minimum solvent rate. So substituting this data, that gives minimum solvent rate as around 2285 kilomole per hour meter square. The next step of calculation is actual flow rate of liquid, which is 1.5 times the minimum. So 1.5 times the 2285, that is the actual flow rate, which is 3427.9 kilomole per hour meter square. Next, we'll move on to the calculation with respect to HTU and NTU. Material balance calculation you need in order to get the exit concentration of solute in the leaving stream of liquid, that means XB. So for that calculation, we are making use of material balance equation. So GM, you have LM calculated, YB, Ya are given data, XA is also given, and we are finding XB through this equation, which is around 0.001667. Then height of a transfer unit calculation, which is V by S by KYA. So V by S is a ratio between gas flow rate, V by S is the ratio between gas flow rate and the cross-sectional area. So we are already given in terms of kilomole per hour meter square. So that will substitute here. Then KYA is also given. By substituting that, we'll be getting height of a single transfer unit. The next step of calculation is number of transfer units. Since the equilibrium line and operating line are straight and parallel, we can make use of the simplified form of equation YB minus YA by delta Y bar L. So for finding number of transfer unit, first you need delta Y bar L. So you are given with this formula YB, YA already we have. YB star, YA star you need. Then only we can find out delta Y bar L. So this YB star is the equilibrium value corresponding to XB, and Ya star is the equilibrium value corresponding to Xa. So how to calculate that? We know the equilibrium line equation. So in that equation, substitute the value of Xb, you will get Yb star. Similarly, in the same equation, substitute the value of Xa, you will get Ya star. So Yb star, that is obtained by substituting Xb and Ya star, since Xa is 0, Ya star is 0. By substituting that, you will be getting delta Y bar L. Then by substituting that in NOY expression, we'll be getting number of transfer unit. So HTU into NTU will give you height of packing, which is 1.6804 meter. Okay, we'll move on to the next problem. A solute is to be recovered from a gas stream by absorption with pure water in a plate column. The entering gas stream contains 2.5% by volume of the solute, and the leaving gas contains 0.1% of solute by volume. A liquid rate of 1.5 times the minimum rate is to be employed. Calculate the number of theoretical plates required. The equilibrium data is represented by the equation y is equal to 0.15x, where y and x are the mole fraction of the solute in gas and liquid phase respectively. So in this problem, it is given that solute is recovered from the gas stream in a plate column. So the type of equipment is plate column. So solute. So it is given generally like some solute is separated by using water as a solvent. So in the entering gas stream, concentration of solute is 2.5%, and in the leaving gas stream it is 0.1%, and liquid rate is 1.5 times the minimum rate. Calculate the number of theoretical plates. And we are given the condition of equilibrium line y is equal to 0.15x. So obviously equilibrium line is a straight line. So when the condition of equilibrium line and operating line are straight and parallel with each other is satisfied, we can have the condition that number of transfer units that is equal to number of theoretical plates. So if we calculate number of transfer units, which is same as number of theoretical plates, which is asked in this problem. Let us write the data given. So solute concentration in the inlet stream is 2.5%. So from that, mole fraction is 0.025, which is YB. Then in the exit stream, solute concentration is 0.1 mole percent. So mole fraction is 0.001, which is YA. Then pure water is used. So there is no solute in inlet stream of solvent. That means XA is equal to 0. The other condition, actual flow rate of liquid is 1.5 times the minimum rate. An equilibrium line equation given, number of theoretical plates we need to calculate. So first we'll find out minimum solvent rate, from their actual rate, then from there we can move on to the calculation of number of theoretical plates. As we have seen in previous problems, through material balance equation, we can able to find out minimum solvent rate. So V into YB minus YA, that is equal to L minimum into XB star minus XA. YB, YA are mole fraction of solute in the inlet stream and exit stream of gas. XA is the mole fraction of solute in inlet stream of solvent. XB star is the equilibrium value corresponding to YB. So B is the gas flow rate and L minimum is the minimum solvent flow rate. So from equilibrium line equation, first let us calculate XB star. Then we will have enough data for finding minimum solvent rate. By substituting YB in the equation of equilibrium line, you will get XB star, which is coming as a 0.1667. So this value we can substitute here for finding minimum solvent rate. So which is in terms of ratio 0.1439. From there, by using the condition given in the problem statement, actual rate is 1.5 times the minimum rate. We can able to find out the actual flow rate of liquid, that is in the ratio of L by V. So 0.21599. Sorry, 2159. The next step of calculation is the actual solute concentration in the liquid stream leaving the plate type column. So again, by using the material balance equation, we can able to find out XB, that V by L, or there is L by V ratio already we have found. YB, YA are given in problem statement. XA is taken as 0 since pure solvent is used. So by substituting all these known data, you'll be getting XB, which is 0.1112. The next step, number of theoretical plates. As I mentioned earlier, equilibrium line and operating line are straight and parallel. In that case, number of transfer units that is equal to number of theoretical plates. So if you calculate NTU value, that is same as number of theoretical plates. So what is the formula of number of transfer units? YB minus YA by delta Y bar L. So you need delta Y bar L in order to find out NTU. Already YB, YA are given in the problem statement. So what is the formula of delta Y bar L? So that is given here. So YB, YA you have, but YB star, YA star we don't have. So what is that YB star? For XB corresponding equilibrium values YB star. For XA corresponding equilibrium values YA star. We have the equilibrium line equation. In that, substitute XB value, you will get corresponding YB star, and substitute XA value, you will be getting corresponding YA star. Since XA is 0, YA star is also 0. Only YB star you are supposed to calculate. So by substituting XB in the formula, you are getting YB star. So once all these data are known, you can find out delta Y bar L, which is 0.003455. By substituting delta Y bar L in NOY formula, you will get number of transfer units, which is same as number of theoretical plates, that is 6.9464. So approximately you need 7 number of theoretical plates for getting the required separation. I hope you have understood all these problems of how to find out height of packing and also number of theoretical plates. Thank you all for listening. Thank you. We'll see you in the next video. Thank you.